13.3 again. We were in chapter 13.3 yesterday as well, but still in chapter 13.3. And chapter 13.3 is going to be on Bernoulli's principle. Yeah. Oh.
Oh, there we go. It's working.
I'll throw it away.
Wait, is it just the brightness? Or
No, it's fine.
Wait, I guess what's that? What you said?
Bernoulli's. Question. What causes pressure? I'm not talking about just like touching pressure. What causes like air pressure? What is the cause? Particles hitting stuff, right? So like there's some air particles moving around, they hit the surface, that causes a force. I mean, it's a real small force, but if a whole bunch of them hit the surface, then it causes a bigger force, right? And so if I had a lot of them clumped really close together, then that would cause a bigger force because they're closer together. And that was called, it's higher pressure because they're higher density, right? Okay, so the way that looks, if I have a surface and a whole bunch of particles floating around above the surface, Bernoullis. Then those particles are in random motion. Okay, what I mean by random motion, they're just moving wherever. Okay, so maybe this one's going this way, and that one might be going that way, and this way, and this way. They're just doing whatever they want. Whee! Okay, they're doing whatever they want. So y'all agree, some of those molecules are heading toward the surface, they'll hit the surface. Some of those molecules are heading away from the surface and they won't hit the surface, right?
Right.
Okay. So if I wanted more pressure, then either I can add more molecules or I could direct all the molecules toward the surface, right? So if all the molecules were heading this way, then they'd all bam, 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 they'd all hit the surface, that'd be higher pressure, right? Okay, and that's what you feel if you hold your hand out the window, okay, and the air is coming by and you feel all that pressure on your hand. That's because all the molecules are now heading towards your hand, right? Or if you're in front of a fan, those molecules are heading towards your face. Okay, so that's higher pressure because they're heading towards your face, right? Okay. So that's wind, right? Wind, a net motion of particles. And if the wind is facing toward the surface, then it was an increase in pressure. What do you think, though, is going to happen if I take those particles and I make a wind or a breeze parallel to the surface? Okay, so now I'm going to have a whole bunch of molecules. Okay, I'm going to have a breeze parallel to the surface. So instead of all of them pointing down, they're going to go in this direction. I mean, they might not all go in the exact same direction, but net direction, they're pretty much going to go this way. I might have some that are rebels. That'll be a rebel. Okay, but as far as net particle movement, okay, net particle movement, they're all pretty much going in the same direction. We see on the diagram on the left, y'all agree that I would have pressure, right?
Yes.
But the diagram on the right, what do you think will happen to the pressure? It's going to decrease because
They're all going in the same direction, meaning off parallel to the surface.
they're going parallel to the surface, so they're not going to hit the surface as often. Okay, so when I have a net movement of particles, then the fluid exerts less pressure.
So net movement of particles, there's that.
Okay, so fluids in motion parallel to a surface exert less pressure. Fluids in motion perpendicular to a surface are going to exert more pressure. Okay, so the direction of motion of the particles is going to be important. But the one we're going to focus on today is the fluids in motion parallel to a surface exert less pressure. That is our Bernoulli's principle. Okay, that's Bernoulli's principle. Fluids. When I say fluids, what am I talking about?
Gases or liquids.
Okay? So therefore, if I have a gas in motion, it could be producing less pressure, or if I have a liquid in motion, it could be producing less pressure as well. Let's break down this this note here of less pressure. Less pressure implies less force.
So current water would produce less
Yes. Depending on what I mean.
pressure. Current's moving like downstream really fast.
Then that way. Well, it depends on if the object's parallel or perpendicular.
It's not the bottom.
Uh,
The bottom of the river.
Bottom
When you're like plant standing up in the river.
Yes. Yeah. Yeah. Okay. Okay. This is really easy to demonstrate. That's really easy to demonstrate, guys. If you will, please, just take a sheet of paper. If this is your face.
Take a sheet of paper. Dang, that's some big lips.
Okay. I want you to take take a sheet of paper and blow and put it up to your bottom lip and blow some air over the top of the sheet of paper. Okay. So if I'm holding it, I want it. Kind of hold it in the corners. I'm gonna put it at the bottom lip and blow over. Huh? No. Okay, you wanna kind of hold it here. Just kind of hold it on the corners. Put it right at the bottom of the top of the bottom lip. Okay, you want it right here at the gap. You don't want it at the bottom. You want it right here at the little gap. You'll see how it lifts the paper? Well, do you see how when I'm doing it, it lifts the paper? Okay, whenever I do it, it lifts the paper. Okay, so what we're seeing, guys, is since there is particle motion above the paper, there's particle motion above the paper. What we're seeing is above the paper, the pressure is less. Okay, so above the paper, I have low pressure. But below the paper, I have high pressure. So therefore, the force on the bottom of the paper is greater than the force on the top of the paper. That makes sense? So it pushes it up. Okay, force is greater on the bottom than it does on the top, so it pushes it up. Oh no? That's exactly how it. Well, don't steal my thunder. Okay. We'll get there in a little bit. Yeah. What now?
Pressure on the bottom is
Same thing as buoyancy. Yeah, pressure on the bottom is greater than the pressure on the top. I mean, it's not. I mean, if you did the other, if you blew on the bottom, would it take it and make it curl down more?
No.
Why does it still make it flop up if you blow on the bottom?
There's less pressure on the bottom than more pressure on top.
Yeah, then there you're pushing it up. I mean, it's still pressure, but now if you're blowing down here, well, yeah, I mean it's higher pressure there because that's a little bit different. Okay, so that's don't think that. All right, where was I? Let me think. Talking about paper. Okay, so this is really hard to see. It doesn't show up all that well, but I'm going to do my best to see it. To hopefully y'all can see it. I'm going to put it on the camera.
Can we go turn our heads again?
No, it's got to be sideways. Okay, so I have a tube here, guys, with water with water that's kind of balanced on two sides, and I know it's crooked, but that's just the best we can do. So I'm going to take some air, and I'm going to blow air across one side of it. Okay, when I blow air, I'm going to blow air across this side here. When I blow air across this side, what's going to happen to the pressure at the top? It's going to be lower. Okay, so there's going to be lower pressure here than there is over here. Okay, so if there's higher pressure here, what do you expect to happen to the water level? It's going to rise. Okay, so it's very, very slight. Okay, because water weighs a lot. Okay, it's very, very slight. But okay, let's see if I can get it to work. Does it? You see it?
No.
This is the last physics class, right?
Yeah.
Okay, yeah, so then waste all the air.
Come over here and do it because they have to be able to. This one I have to tilt it back. Well, that's.
That's when we push
It
down.
works. Yeah.
Is it working?
No.
There we go.
See it just a little bit.
It's all a little jiggy.
You should have seen when I pushed the air, it should have just risen just a little bit.
Yeah.
Okay, just a little bit. Now, I mean, it's not like I said, it's not going to be much. And that, no, that one I blew into. I mean, yeah, if I go there, blow it down in there, it's really going to move. Okay, that's.
Yeah, they
And that's-
stick the straw inside the water.
No, that's just gonna, that would splatter water all over the place. Alright?
Nuh-uh, it would be cool. No,
Yeah,
put
that's-
the straw in the water.
It's just gonna blow bubbles. Are we still entertained by bubbles?
Yes.
Do it.
I'm just visualizing you in the cafeteria going with your straw. No, we're not. We're hopefully not. Still entertaining ourselves by blowing bubbles. Bubbles. That's what y'all are supposed to do. Okay. So we see this. We see this effect used a lot of different places, and frankly, I was trying to decide what examples I wanted to use because there's so many of them, and I just decided just to do all of them. So we're just going to talk about all of them. And so the first example I wanted to talk about is with prairie dog nests. Okay, so prairie. Is that funny?
Hey, you know they have prairie dogs in the zoo, so we should take them.
Yeah. No, I think y'all should take a field trip to the zoo. No, notice y'all. I need to sit for this.
Yeah. Did you zoom out?
Do I need to zoom out?
I don't know, I was just asking if you did.
Okay. Nothing. All right. So let's say I have a little hill here, and there's some grass. It's a pretty hill.
You can like speed this up.
No. And so in a prairie dog nest, they will tend to have lots of tunnels. So they might have an entrance. We'll do that. We'll do their tunnel in red. They might have an entrance here and here, and maybe it goes to some tunnels. Maybe these connect. Okay. I don't know the anatomy of a prairie dog nest, but they tend to have several entrances. And I'm not going to draw a prairie dog because that would not be pretty. Let's say you get on one side of a building, guys. You're standing here, and a breeze comes by the building. Do you feel the breeze?
No.
Start to the end. No. Okay. No, you don't feel the breeze. Why not? The building blocks the breeze. Okay. So let's say a breeze comes by this hill. Okay. If the breeze goes by the hill, does the breeze pass through that hole or pass over that hole?
Yes, it passes over.
The lower hole?
No.
No, because the hill blocks the breeze, right? So in other words, I have air moving above the top hole, but not the bottom hole. So what can I say about the air pressure here?
It's greater.
It's lower. And since there's no movement here, the air pressure will be higher. Air always tends to move from high air pressure to low air pressure. So what we see, guys, is a breeze will go through that tunnel. Okay, so that's how they keep their tunnel ventilated. That's how they keep it cooled. and make sure there's plenty of oxygen in the in the tunnel. Okay, that's just because they have two entrances. One is on a hill and one's not.
And they know all about Bernoulli's principle.
Yeah, prairie dogs are actually very smart. They're the physicists of the animal community.
I'll have you know that my teacher in college.
I don't know. In fact, our guest speaker here. No.
That would be awesome.
I wanted to make a sound. but I
Prairie
don't
dog.
think Prairie dog snake.
Okay. What now? What?
I'm just thinking of like hurricane force winds going over a prairie dog. All
No, I mean, it's not like if a baby prairie dog walks right here, it's going to get shot up the hole. I mean, that's not really what's happening here. Okay, but it's just like a loop. It just gets shot out that one, and it comes back in this one, and it just gets shot out that one.
It's like a never-ending cycle.
No, that doesn't happen. But the main point, using Bernoulli's principle, and they don't know what Bernoulli's principle is, but I'm assuming that's probably in their genes to do that. But that's in their instinct, yeah. Humans, we use Bernoulli's principle as well. It took us a little bit longer than it did the prairie dogs, but we finally figured it out. If I have an airplane, y'all know, guys, an airplane uses wings in order to generate lift and move upward. Okay. If I were to take this wing and look at it from the side, then the shape of the wing we would see would be something kind of like that. Okay. So like a cross section of the wing. Okay. If you cut it in half and looked at it, that's what you'd see. Okay. So if I took this wing and I cut it off, I'd see that on the end. Okay. And this design here is called an airfoil. Okay, and an airfoil, guys, is used to generate lift. When the plane moves through the air, let's trace two different molecules of air. Let's say I have one molecule of air here and one molecule of air there. Okay, when the plane comes through, those air molecules are going to have to get out of the way because two things can't occupy the same space. So essentially, they're going to follow this path. One is going to go up across the top, and one is going to go around the bottom. Following me so far?
Yes.
Okay. I mean, the air molecules aren't changing location. They're being displaced temporarily, and they go back to where they were. Right? So this one, it has to kind of go, and this one goes across the bottom, and then we end up, and they're in the same place. Okay? So it moves through, but one has to go that way, one goes the other way. Which one moves a longer distance? The one on top. Okay? So since the one on top moves a longer distance, I know that it's relatively moving faster. Okay, so the velocity on top is considered to be faster, and the velocity on the bottom is considered to be slower.
Yes.
Velocity of air creates low pressure. Okay, so on the top I'm going to have low pressure, and since on the bottom I have low velocity, I'm going to have high pressure. Okay, since I have more pressure on the bottom, that means I have more force on the bottom. And so I end up with a net upward force. Okay?
Yeah, it helps out a lot.
That actually,
I can see that. Oh, calm down. Okay. So that ends up with a net upward force. That's one design for an airplane wing. That's the one that we use. Okay, there is an alternate design. It's real simple. I would cut this wing in half, and I would have that. Okay. So in other words, if this is kind of the same concept as if you're driving along and you put your hand out the window and you do that. Okay. If you're going like that, whatever, and you go like that, and your hand gets pushed up. You know what I'm talking about? Okay, so there, air molecules are coming, they're pinging off, right? Okay, and so that's creating a high pressure on the front, and not really as much on the bottom because they're going that way. They're trying to fill in that gap. Okay, So this is a much less efficient way of producing lift. Can you tell me why that's a less efficient way? What direction is the pressure on this one? If the plane is moving to the for y'all, if the plane is moving to the right, then the pressure would be to the left. So in other words, it's resisting the motion of the plane. Does that make sense? So that's essentially taking this plane and slowing it down. This one, the pressure is.
Is that why they lift those flaps?
Yeah.
Like,
Mm-hmm. Yeah, we'll get there in a second. Okay, what have I told you about stealing my thunder? Okay. This one, the pressure is up and down, so this one does not create as much drag. Okay, so when a plane is taking off, it's not going as fast as when it's cruising, right? I mean, it's going slower when it's taking off. So it's creating more lift because it's got to lift itself up, and because when it's going straight, it's not going up and down; it's just going flat, right? So when it's taking off, it's got to lift itself up. So how do you think it generates more lift when it's going slower? It just changes the direction of this. Okay, it essentially combines this design. When you're going slower, it just and twists that a little bit. Okay, have y'all ever noticed, when you're coming in for a flight, you're cruising in, you're starting to move slower, and then you hear like kind of sound, and then it's like, you know what I'm talking about?
I wish they screamed.
That's the fun part.
So it's but you know what I'm talking about, right?
Yeah.
Okay, that's because we are taking that flap and we're moving it down, so that's creating more drag. Okay, now it's increasing the lift so that you can move slower, but it's creating more drag and taking the plane and slowing it down. Okay, so it slows the plane down, but it creates more lift so you can stay in the air.
Have you ever been on a transcontinental flight?
Mm-hmm.
You have?
Mm-hmm.
Like, have you ever, I don't know, whenever I went to India, it was like, 17, 18 hours. And then coming back, I'm just making up some number, it's a lot longer than that, I'm sure. But then whenever we were coming back, the exact same route, it actually took longer because the plane had to go against the wind.
Yeah, for the Earth, the prevailing winds of the Earth are easterly. The prevailing winds, at least the northern hemisphere, I don't know about the southern hemisphere, but the northern hemisphere prevailing winds are easterly, so when you're going that way, you're going with the wind, and when you're coming back, you're fighting the wind. I know when I went to Europe, it was like an extra hour, I think.
I think it was just 3 hours.
Yeah.
Like
Not a helicopter's great, but
Same thing. They have that, and so but instead of the helicopter's motion making the air particles move, they take the blades and spin the blades, and that makes the air particles move. So the blades would be shaped like that. So you can't take the blades and spin it the other way. Okay, if you spin it the other way, you'd push you down. Okay, so you gotta spin it in one direction because they are also like that. One more place. This is one more example. I was in my car, and this is going to be my car from the top.
Are you gonna drive into a dog viper?
Yeah, that way. Evidently, I drive a square. We'll let that be my car from the top. And I had both windows open. I had the driver's side window open and the passenger side window open. Okay, and I went around a curve. Okay, so when I went around the curve, what you should notice, guys, is one side of the car is going to be moving faster than the other side of the car. This side of the car is farther out, so it's moving faster than this. Okay, so in other words, the air over here is moving faster than the air over here. So that ends up creating on this side, since it's moving faster, lower pressure.
So wait.
And on this side, I end up with high pressure. So what you should feel, guys, is when you go around a curve, when you go this way, you should feel a breeze coming through your car in that direction. And when you go around a curve in the other direction, you'll feel a breeze going through your car that way.
So
if you only have one window down.
If you only have one window down, you won't feel anything. Oh, you might feel a little something, but you won't feel as dramatic. Okay, this I guess I shouldn't talk about this. This same principle, what smokers use in cars to help keep the car clean from smoke. They take that window and lower the window just a little bit. Outside of the window, there's a lot of air that's moving at high velocity. So in other words, there's low pressure outside. Okay, so that makes air go from the inside to the outside. Oh, it's time to leave already?